So far, we've gone through the method of time and transfer constants, and we saw that in general, if you had an n-order system, meaning you have n energy storing elements, you can treat them as you can treat the system as a system with no dynamics. And all these energy storage elements being basically attached to n different ports. We have Ci, Cj, and so on. And this is x, the input, y, the output. So we saw that we did look at this several different ways, right? We saw that, first of all, this system we looked at the first order system and we analyzed it, and then we used this system to determine the overall transfer function. So we know the overall transfer function of this thing can be written as A0 plus A1s plus A2s squared way up. And in the denominator, you can have 1 plus B1s plus B2s squared all the way up. And we did determine this for an n-order system. The A1 and B1 to be, we determined A1 to be Hi tau I0 sum over all the energy storing elements, and B1 to be just simply sum of the zero value time constants. And so B1 was the sum of all the zero value time constants, and zero value time constants were the time constants associated with individual elements when all the other elements were zero value. Now, if they were capacitors, we opened them. If they were inductors, we shorted them. And then we looked at the resistance seen across here. So, for instance, tau 10 would be resistance seen here, R10 times C1. And R10 is the resistance seen across here when all these other elements are zero value. So all of these R value calculations are low frequency calculations because there are no energy storing elements when you're looking at each one of these cases. So these are the zero value time constants. And these are the same zero value time constants, so you can reuse them. And these are what we call the transfer constants. These are the first order transfer constants, which are basically the ratio of the input to output when all the elements, except for element I, are zero value, and element I is infinite value. So for instance, in this case, this is capacitance Ci, this one is shorted, everyone else is zero value. Basically, the capacitors are open and the inductors are shorted. And you look at the low frequency transfer characteristic from the input to the output, which is what we call zero transfer constant, because it's a constant, it's not a function of frequency at this point. So we saw that those as Hi tau i's, and we saw that it's the sum of these, and we did this, we proved this last quarter, and that basically gives you the overall response of the system to the A1 and B1. So this was basically what we derived so far. Now the next step up is going to be determining the higher order time constant, higher order terms, and I'm going to tell you what they are, and we will derive them in steps as we go forward. We'll spend a little bit of time specifically on the second order system first, although we can go and directly do the nth order system. But doing the second order system gives you a little bit more feel for how these terms look like, and then we'll look at the nth order system. But let me give you what the answer looks like. So the answer is that A2 and B2, in the case of B2, it's a double sum over tau I0, tau Ji, where basically I smaller than J, smaller than or equal 1, N, and greater than or equal 1. Basically, you go over all combinations of I and J's, where J is greater than I. So you don't, if you have done 1, 2, you don't do the 2, 1 in this case. Of course, you can do the 2, 1 if you want instead of 2, 1. You will see how that works. But so what this means, these are zero value constants, what we call the zero value DVTs. Now these guys, we talked about them very briefly. What are these time constants? This is basically the time constant associated with the J element when the I element is infinite value and everything else is zero value. So this is a different low frequency calculation. This is a different resistance. So that resistance basically you can show it as RJI, which basically means that the resistance seen by value. So you short this, so this can be a different resistor. Right? Now, remember, in our notation, one thing that makes it easy to understand is that anything in the superscript, any index in the superscript is the index of an element being infinite value. So if you have I here, it means that element I is infinite value. If you have I here, it means that element I is infinite value. For this calculation. And if you have 0, it means that nothing is infinite value. Everything's 0 value. So that makes it easier to follow the notation. Anyhow, so that's B2, and then A2 is a similar sum with the difference that you have Hij in front of each term. And what that means that Hij is the transfer function from the input, the transfer constant from the input to the output, when both I and J, elements I and J are infinite value. And everything else is 0. And then, as you can imagine, now we can imagine B3 is going to be a triple sum tau I 0, tau Ji, tau Kij over Ijk, and I'm going to show it like this. And you know what that means. It's smaller than or equal n, greater than or equal 1. And then same thing here with an Hij in front, but all the other terms are similar. And this is, as you can imagine from the notation, that should be kind of obvious. You should be able to tell what that means. What does that mean? What is tau Kij? Does anyone want to take a job?
Time constant seen from element time constant of element K when the elements I and J are infinite value.
And everything else is 0 value. Right. So now you have two elements that are infinite value. Then you can go on, and of course in general, Bn and An, no, not this n, basically. This would be multiple sums of I, J, n, and tau I0, tau Ji, tau Kij, all the way up. The next one would be tau Lijk, etc., etc., etc. And they look pretty messy, but they are not as bad as they are. And then here you have basically I, J, K, etc., etc., etc. in front of taus. And we'll use them. When we use them, we will see them more clearly. So these are the results. This is basically the end result. But okay, how do we arrive at these? Well, I'll take a little detour here. We'll go and do the second order system, which we could directly go and do this B2 and A2, and then that would subsume the second order system. But I think it's better to do the second order system because in that context you will see more of a you get more of a feel like for that. So in a second order system, let's say there are just two capacitors for now, and then you can see how it generalizes. It's very simple to generalize to inductors. So you have a C1 and C2. You have two ports. This is X and this is Y. No dynamics here. So what do we know about this transfer function? What can you tell me about this transfer function? The transfer function of this thing has to look like this. A0 plus A1s plus A2s squared divided by 1 plus B1s plus B2s squared. Right? What do we know about this? From what we've proven so far, which is basically A1 and B1. We had proven the first two terms, right? The B1 and A1 terms. So we knew that, what is A1? Or B, what is B1? Let's start with B1.
Tau 1 plus tau 2.
Tau 1 0 plus tau 2 0. The two zero value terms. And A1 is H1 tau 1 0 plus H2 tau 2 0. Fine. Now how about A2 and B2? Well, let's find out. So in general, how can I write this? What can I know? What do I know about this transfer? Well, I know A1 and A2, so fine. So and what do I know about A0? A0 is H0. So I know that this is H naught plus those two terms. Let's say H1 tau 1 0 plus H2 tau 2 0 S plus. Now, what do I know about this A2 term? We know that if you have only capacitors, where does the term S come from? Only the capacitors can generate a term S. And they always have to come in conjunction with a C. So you have a CS. So you can have a C. So in the most general case, actually, if I wanted to do this, and I will do this only once, I should have anything of the second order of C. So basically I can have C1, C2, and I can have C1 squared or C2 squared, right? So I could have all three of these. But I argue that you can't have any of these two, either of those two, only you have the first one. Why? Because this, when I wrote this down, I didn't make any assumption or I didn't make any statement about what the values of C1 and C2 are. Right? So this has to be valid for any value of C1 and C2, including 0 and infinity. Now, if that's the case, if I set C1 to 0, this term, these two terms become 0. But this term remains non-zero, right? Let's say C1 is 0 and C2 is non-zero. So, but if C1 is 0, I should get a first order system. Because I only have one capacitor. But that gives me a second order system, this term. So by this argument, this cannot exist. It has to be only the multiple cross terms. The same argument, of course, there's no preference for indices 1 and 2. You can make it for the other one, but this one cannot exist. So the only thing that exists or remains is this term. So this only can have a C1 and a C2 and S and some coefficient in front. So we call this alpha 2, 1, 2, C1, C2, S squared. And the same argument applies in the higher order terms. You can only have like C1, C2, C3. You can't have C1, C2 squared. Because in that case, basically you can get, by setting 1 to 0, you can get a second order system out of a first order with one capacitor, basically. So, and in the denominator, I have 1 plus tau 1 0 plus tau 2 0 times S, fine, plus similar argument here, beta 1 2, C1, C2, S squared. So this is the most general case. So the only thing that's left to be determined, the two things that are left to be determined are alpha 2 and beta 2. The subscripts of alpha, these are intermediate variables. By the way, the derivations you don't need to remember, but it's good to see them once, at least see where they come from. So this is a derivation essentially. So these are intermediate variables, we won't use them later, but just to help us work it out. So this is the H of S. So what can I do to determine beta and alpha? So let's assume first that C1 is going to infinity. If C1 is going to infinity, what happens? What kind of system do I have? What that corresponds to? That corresponds to a system where this is basically short circuit. So this is a short circuit. And it's a first order system. What is the time constant of this first order system? We know, right? It's whatever that time constant we can call the time constant of this system, we call tau 2 1. 2 because index of the index of the capacitor left is 2, and 1 because the port 1 is short. So that's by definition we define tau 2 1. Now what is tau 2 1? It's the resistance seen by this guy times the capacitance, right? And the resistance seen by that guy obviously should be called R21 in our notation. That's C1. It's the resistance seen from port 2 when port 1 is infinite value. Right? So this is really the definition of tau 2 1. Okay? So that's the time constant. But we know, so let's see what happens to this equation when C1 goes to infinity. When C1 goes to infinity, in this case, then H of S becomes what? So
that should be C2, not C1.
The R21, C2.
yes, this is C2, yes, thank you. Yes, C1 is infinity anyway. Thank you. Okay, so that's good. Yeah, so what happens So if this goes to infinity, this would not matter because this is the one that goes to infinity, and this is the one that goes to infinity, and these guys are left. So this is what will be left. So these guys don't matter. This is what will be left. So it becomes H1, C1, R10, which is tau 10, times S. This term will not matter when C1 goes to infinity. Plus alpha 2, 1, 2, C1, C2, S squared, divided by this one. In this case also this one would be the only one that would be left, would be C1, R10 C1, so I'm writing it as R10 C1S plus beta 212 C1 C2 S squared. Right? C1 going to infinity, that's what will be left. But now I notice that everyone has a C1S. So I can basically factor it out or eliminate all of this, the C1S, the C1 and S, C1 and S. Okay. So that's what will be left. So what is left is, let's rewrite it one more time. And I can factor H1 out. So if I want to factor H1 out, I will get basically, and I can divide by R1. So 1 plus, okay, by R10 basically. I divide the numerator and denominator by R10, so I get alpha 2, 1 over R10, C2S divided by 1 plus beta 2, 1, 2 over R10, C2S. Fine.
There must be H1 in the. Yeah, in the second term of the numerator, you have to have H1.
Oh, okay. Yeah. Going to factor it out. Yeah, that's right. So basically, that's what I would be left with. Now, okay. So, but now I know what this term is, right? Because this is the time constant of this new first order system. I've created a different first order system, a new first order system. This is the time constant of the first order system, which has to be equal to that. So I will equate those two. So I basically say beta 2, 1, beta 2, 1, 2 is going to be, okay, or I can write it the way that is, and then do that. R10 is equal to R21 C2, and therefore C2's cancel. I am left with beta 2, 1 being R10, R21. And if I plug it in here, I will see that this whole thing becomes what? R10, so you can write this whole thing, or B2 essentially, is going to be R10, C1, R21, C2, which is tau 10, tau 21, which is what we expected. And then I have to determine alpha 1. Alpha 2, 1, 2, 1, 2. So how do I determine that? Then I set both C1 and C2 to infinity and determine the transfer function, right? So if I do that, both of them are there. Basically, this is the definition of H12. H12 is defined as H of S when this happens. The transfer constant. H12 is defined as the transfer function when C1 and C2 are both infinite value. In this case, it could be a zero order system. It could be a DC transfer characteristic. Okay, so that's H21. So, but what is that in this expression? Well, this is what happens when one of them is infinity. If I set C2 to infinity, what do I get? All that would be left with is the ratio of these two things. Right? So from that, what do I get? I get, so R10's cancel. All I'm left with is alpha 2, 1, 2 over H1 beta 1, 2.
Also, you have one H1 out.
I'm sorry?
You have factored one H1 before.
Okay, yeah, and this H1 cancels that H1. That will, the the factor in front would eliminate that because there's an H1 here, which will remain. So these ones cancel. So it's just a ratio of these two. So basically, alpha 1, 1, 2 is simply beta 1, 2, beta 1, 2 that we just calculated times H1, 2. So it would be the same thing. This term would be exactly the same, except for the fact that it would be H1, 2 times tau 1, 0, tau 2, 1, which is A2.
That is alpha 2, 1, 2.
Yes, alpha 2, 1, 2, yes, thank you. It's an intermediate variable, it doesn't matter, but yes, that's correct. So, this basically shows the special case of a second order system. So in a second order system, so again to summarize, so this was the derivation. But to summarize, what that tells you that in a second order system, A2 is simply H12, tau 10, tau 21, and B2 is tau 10, tau 21. You don't need to remember the derivation, but the result. Now, one thing that I threw out this thing, when I was starting with this, I wrote this as alpha beta 2, 1, 2, right? I could have written this as beta 2, 2, 1. There's no preferred order of indices, right? Indices are arbitrary. I could have chosen this to be C2 and this to be C1. And every one became 2 and every 2 became 1. So that tells me that something, right? That tells me that beta, there should be some qualities, some properties for beta, right? So for instance, beta 1, 2 should be equal to beta 2, 2, 1. And same thing with alpha. Alpha 1, 2 should be equal to alpha 2, 2, 1. What that implies is that when you look at this, it means that R10, or I just have it right here, R10, R21 has to be equal to R20, R12. Now, while these are just indices here, but these are two different calculations. It means that you can calculate this resistance, which is the resistance seen by this guy when this is infinite value, or you could calculate the resistance seen by this guy when this is infinite value. And this product should be the same, and you will see that they are the same when you do the calculations. I'll just show you some real practical examples. And moreover, what that means is that tau 10, tau 21 is equal to tau 20, tau 12. And this is the one that you want to remember. So these are the things that you want to remember from this. Now, remember, it doesn't mean that individually tau 10 and tau 20 are the same. They are generally are not. But their mutual products will always be the same. And it's very useful because it gives you alternative ways of calculating these things. Okay, so much for the derivation. So now, what do we do with this? Let's talk about a couple of examples, right? Let me just go over a few. And by the way, one more thing. If you have inductors, everything is the same. So taus, for capacitors, obviously, we calculate them. If you have inductors, then the tau, any of the taus would be basically the inductor over the associated. So let's say, for instance, tau ij would be Li Rij. Just instead of multiplying by the resistance, you divide the inductance by the resistance. It's L over R. Time constant is L over R is equal to R. So it applies for both inductors and capacitors. Okay, so let's do an example. The first example, let's pick a simple example. A band passive circuit.
Out here.
By the way, I just already said this is a bandpass, but how could you tell this is a bandpass?
Well, we can
There are different ways to think about it, but go ahead.
evaluate the behavior of the circuit in frequency.
Yeah, but no, I mean without evaluating.
No, just setting for zero frequency, both capacitors are open, so
Right.
there's no output.
So at DC, there's nothing goes through because of this guy. At infinity, this is shorted, so nothing gets to the output. So at 0 and infinity, your transfer function is infinity. Your way of thinking about it is also valid. You say it's a low pass followed by a high pass. So that's also valid. There are different ways to think about it. But again, independently. I don't have a loop that will limit me in that case. How many zeros? There's one element, infinite valuing of which results in a non-zero transfer function. This one. So 1, 0. Left half or right half plane? Left half plane. Why?
Doesn't change.
It doesn't change the polarity, exactly. So make sure this doesn't change. So we know I'm expecting 2 left half plane poles, 1 left half plane 0. And if I get anything else, then I've done something wrong. So, alright, so that's actually good. So what is tau 1, 0? I have to determine all the zero value time constants. Tau 1, 0. What is it? You should be able to do this by inspection. What is the resistance seen by this guy? When this one is infinite, open, zero value. RA. Right? What is tau 2, 0? Resistance seen by this guy when this is zero value and this is null.
RA plus RB.
RA plus RB, right? You see RA on this side, RB on that side. So that's your P1. You determine your P1. And then you need to determine one of the tau 1, 2 or tau 2, 1. Right? In this case, I'll do both to show you that the product is the same, but you only need one. So let's do one first. Which one looks easier? To me, this one looks easier because if I short this, then I don't have to worry about anything on this side. So I pick the easier one. If I were to do this in one shot, So I calculate tau 2, 1. Basically, what is the resistance seen by this guy when this is short? It's RB. So at this point, I'm done for the denominator. And let's do the numerator part. What is H0? 0. Nothing goes through.
RB over RB.
So what is the only non-zero H? Transfer constant. It's H2, right? Because this has to be shorter, right? So this is infinite value. What is the gain? It's the resistive divider. And the rest of them are 0. And the reason H12 is 0, so H1 is obvious why it's 0. H12 is 0, both of them are shorted, but this shorts here. So you basically short the output to ground. So at this point, I'm done. I mean, I can try to plug it into the equation and get that form that I want. And in a second, but this is all I need. But now for the sake of discussion, let's do the opposite one. Let's do tau 1, 2. We don't need this. But let's see if that equality holds. What is tau 1, 2? Is the resistance seen by this guy when this is shorted? What do you see? See RA parallel RB, right? You see RB on this side and RA on that side. So you say RA parallel RB. And I would keep it like that for as long as I can, unless I really need to write it in a different way. Okay, so I claimed that tau 1, 0, we actually proved, but let's see. This should be equal to tau 2, 0, tau 1, 2. So let's calculate this side. Tau 1, 0, tau 2, 1. Tau 1, 0, tau 2, 1 is RA, RB, C1, C2. And let's see if it's equal to, now, tau 2, 0, this guy, times tau 1, 2. What is this? Now we have to expand this. This is RA, RB divided by R1 plus RB. RA plus RB, which cancels that one. So I'm left with RA, RB, C1, C2. Right? We shouldn't have anything. It could have been extremely surprising if it was otherwise. It basically disproves algebra. But just to convince ourselves that we haven't made a mistake in the algebra. Okay, alright, so that's what we have. And by the way, this happens to be our V2. So we killed two stones with one bird. I mean, two birds with one stone. But, okay, alright, so what we have here, so the transfer function looks like this. So H0 is 0. So the only term we have is this times that, times S. Right? A1 is the only non-zero term, because this is the only non-zero H. So I have, this times that is easy because this cancels that, so so I'm left with RB C2S divided by, I'm still trying to envision killing two stones with one bird. Difficult process. So, and then tau 1 and tau 2, basically this gives you RAC1 plus RAC2 plus RBC2. I mean, this is basically pretty much most of the times a useless exercise to write it in this form, but we will do it just to convince ourselves. And then B2, we have already calculated to be RA, RB, C1, C2, S squared. That's your transfer function. You see a bandpass transfer function. You have, and it's consistent because you have two poles and 1, 0, all of them left half plane. So what you see is that you have left, you basically have a transfer function, obviously, that looks like that. More or less. Okay? Any questions on this?
Well, how do you say that the 0 is left half plane? Since
Left half plane, yeah, it is left half plane.
It's a 0, why?
Well, okay. It's a good question. Is the origin left half plane or right half plane?
No idea.
Okay, so it could be the origin or the left half plane. Okay, so that's like the greater than equal or just greater than. So, but yeah, so it could be at the origin in that sense. All right. Now, but that's a good question. So this is one example. It's like somewhat of a trivial example. So let me do a little bit, I mean, less trivial still of this example once you do it. Let's do a source follower. Let's say you have R2, you have R1 at the input, the in, the out, and then you have two capacitors, of course CGS and CGD, but we call them C pi and C mu. Doesn't matter what you call them. That makes it easier because I don't want to have double indices essentially. It makes my life more difficult. So you can call them C1 and C2. Okay, or compound indices. Okay, so how many poles, how many zeros? How many poles? 2 poles, correct. And how many zeros? 1, 0, correct. Only shorting of this one. You can't simultaneously short this and that and get a non-zero transfer function because this shorts the input essentially. And shorts the out. Basically, if you simultaneously short both of them, you short the output to ground. So, and left half or right half? Left half because it doesn't change the polarity. It still remains non-inverted. Okay, so we already know that stuff. But if you wanted to know where they are, what do you do? Okay, so we have to go, well, H0 is probably the first thing we calculate all the time. What is H0? H0, the low frequency transfer function. Remember the voltage divider, you have Rn here and R2. So it's R2 over Rn plus R2. Which, if you are keen on writing it like everyone else, which I don't think is a good idea, you just do it for the sake of argument. You can write it this way. You can multiply by Gn, the numerator and denominator.
Why not to R1?
Well, this is a source follower, right? This is a. So think about it. This is the
Oh, okay.
small signal. This is a MOSFET, right?
Yeah, I thought it's CPG.
So this current is 0. So this voltage is the same as that voltage, so it doesn't matter. From a small signal perspective. And, okay, so that's H0. Now, what other H I have which is non-zero? It's H pi, right? What is H pi? When pi is shorted, C pi is shorted, what happens? What is the gain? It's the voltage divider between R2 and R1. So it's R2 over R1 plus R2. Okay, fine. But now, the time constants are really the ones that are more important, essentially, generally, typically. So, what are the taus? So we have tau 1, 0, or tau pi 0. What is tau pi 0? The resistance seen by C pi when C mu is 0 You remember we had these 3 calculations that we did last quarter, right? So it's what you see here in parallel, right? So in this case, you see basically R1 plus R2 divided by 1 plus GMR2. I'm using those expressions. And then we have tau mu 0, which is, you guys tell me what tau mu 0 is.
R1.
What is the resistance seen by C mu when C pi is up?
R1.
Right, because you see infinity looking this side, so you just see the R1. So you're looking into the gate. It's a low frequency calculation, remember. So it's basically R1 C mu. And what is, now I need one more time constant really. So which one makes my life easier? Shorting of which one makes it easier to calculate. That's the way I should think about generally, right? If I short circuit, actually, both of them are easy relatively, but I actually like to do, both of them are easy, and we will do both now, but I think, I believe it's actually, I would like to do tau pi mu, and here's the reason I'm going to do that. Because my tau mu 0 is very simple, and this gets multiplied by that. So it increases my chance of having to do less manipulation. But it's a call, and you can always do it either way. So if you short this, what do you see? What is the resistance you see?
R2 parallel with R.
Are you sure?
Yeah.
Okay. So if you do that, what do you see? If you short it here, you see R2 parallel Rm. Correct. Because you see Rm up there and R2 down here. Now, which we can write basically as Rm R2 over 1 plus Rm plus R2. Let's do the other one, just in case. Tau mu 0. This is unnecessary, again, but just like to convince ourselves even more this is the case. So what is tau mu pi?
R1 plus R2.
R1 parallel R2, right?
The parallel R2.
Right? So it's R1 parallel R2, which is basically R1 R2 over R1 plus R2. Okay, so let's see if the mutual products are the same. So I'll do this one first, which is the one I targeted.
Did you forget the capacitance?
Yes, I forgot the capacitance. Thank you. The capacitance are easy. It's always there. Subscript.
Both.
Say again?
Uh,
Okay, so, and this one I forgot the capacitor too. So let's do this one and that one, which as I targeted, so that's basically tau mu 0, tau pi mu. And I promise I won't do this every time, just a couple of times. So you get basically R1 times R2 parallel Rm times C pi C mu. And we can do this one, this times that, which gives me tau pi 0, tau mu pi. Tau pi 0 is R1 plus R2. I multiply and divide, I multiply the numerator and denominator by Rm, so I get Rm plus R2 times this guy, which is R2, R1, R2 divided by R1 plus R2, C pi C mu. This cancels that, and then you can take this and that and that, and that gives me R2 parallel Rm, so it becomes R1 Rm parallel R2, C pi C mu. You can see this one gave it to me with less effort than that one, because I kind of planned it ahead of time. I said, this is a simpler expression, so I want that to be part of my product. So I can just have this. At the end, you get the same result. And I will keep it in this form for as long as I can. Because it's a lot easier to deal with that. So that gives me something, fine. So let's write the denominator. So the denominator here, or let's write the B1 and B2. B1 is going to be the sum of these two terms, so it's R1 C mu. I want to get some sort of meaningful conclusion out of this. Otherwise, just algebra. And B2 is going to be R1, Rm parallel R2, C pi C. Okay. And A1, which is the only non-zero term, is going to be this guy times that guy. So as you can see, this cancels that. So I'm left with R2 over 1 plus Gm R2, which I again like to write as Rm plus R2 times Rm C pi. So I know everything I need to know. This basically is everything I need to know about this transfer function. But now so this is basically, you can see I have 2 poles and 1 0 and all that. But I want to learn more about the behavior of this thing. So what do I do? Well, let's make an assumption. Let's assume that R2 is greater than or much greater than Rm, which is the reasonable assumption, and R1. Let's say you have a small source resistance. Let's see what happens. If this is the case, then what happens to these expressions? This term becomes what? This whole thing. Let's write this. This guy is dominated by R2, right? So it becomes R2, these two terms won't matter, so it becomes basically 1 over Gm. So it becomes R1 C mu plus Rm C pi. Fine. And B2, this becomes, so this is an approximate, and approximately this becomes, this basically between the two of them, this guy will dominate. So this becomes R1 Rm C pi C mu. And this term becomes approximately, in this case again, this becomes 1, so it becomes Rm C pi. So my transfer function looks like this, in this case. It becomes Rm C pi
You also need to modify the H0 for this one.
Correct. My H0 becomes what?
1.
1. So my transfer function becomes 1 plus that, approximately. 1 plus R1 C mu plus Rm C pi S plus R1 C mu Rm C pi S squared. Fine. But now I notice one thing about the denominator. It can be factored. So it can be factored as 1 plus R1 C mu S times 1 plus Rm C pi S. But the numerator is 1 over Rm C pi S. Begin with, with this approximation. So these guys cancel. So I'm left with what? Effective in this case, 1 pole due to C mu and R1. What does that mean? What does it mean? Do you remember when we did this before? We said that when we did it just with the C pi, we had a pair of poles and zeros. We had a pole and a zero. And we noticed that they were close to each other. Which one happened first was like a question of the relative sizes of R1 and R2. So what I've done in this case, basically I've made them equal. So this is a pole associated with the C pi. So these were high frequency poles. 1 pole and 1 zero, right? High frequency pole and zero, both left half plane. So they cancel each other out for the most part. But the response of this stage is really what it tells you is dominated by C mu as the input. So this is what really determines its frequency limitation. The first order. It's the C mu and R1, not the C pi. And this also goes back to our way of thinking about the Miller effect. Because the effect of this capacitor, if the gain of this stage is large, which basically that's what it means when you write R2 is greater than Rm, makes the gain close to what, right? So the gain from here to there is close to unity. So this side goes up, that side goes up too. They go up and down. So you see basically a lot less string across the capacitor. So the effect of that capacitor is very attenuated a lot. It's less significant. And C mu, that becomes a more dominant values, that's what happens. Okay, any questions? There's a calculation of the output resistance of this, an equivalent model of the output resistance with both C pi and C mu in your handouts, which I recommend you look at. I'm not going to do that calculation, it's just long. And but that gives you a sense. But I'm going to do something else actually. I'm going to do the output, the input impedance when you have a capacitive load. So let's stay on this follower and do something that has a little bit more of an interesting process. So let's say you have an R1. Let's forget about C mu in this case. And let's say you just have C pi. And say CF. Let's even do this. So I apply a test voltage Vx or Vn and I measure Ix. What is the quantity that I'm measuring, by the way, if I do this? What am I measuring? So I'm interested in determining the input impedance, for instance, let's say. Or am I calculating the input impedance now? What is my independent source? The voltage source. What is my dependent variable? Current. So I'm actually calculating what? The ratio of the current to a voltage. So when I apply test voltage, I'm automatically calculating what? The input admittance, not the impedance. So that's what I'm calculating. And as long as I keep it consistent, everything is fine. As we talked before. But if you mix them up, then everything goes haywire. So I'm calculating the input admittance, fine. So first, I have to determine the Y naught. What is Y naught? What is the Y0? Basically, when all the capacitors are 0 or open. What is it? 0, right? Because the input impedance is really infinity. The input resistance is infinity. It's the input conductance. There's no current flowing through here. And over here, right? So Y0 is 0. Okay. Now, is there any Y that's non-zero? How about Y pi? What is Y pi? Do I see non-zero current if C pi is shorted and this one's open? No. So it's 0. What if CL is shorted and this one is open? Do I see anything? Still no. What if both of them are shorted? What do I see? How much current does go through this thing? If both of them are shorted.
You're shorting your voltage source.
So how much current does go flow?
Infinity.
Infinity, right? So it's infinity. Fine, I can get an infinity, but then I'm sure usually when this happens, I'm going to get a time constant that's 0, so I'm going to get 0 times infinity. I know up front I'm going to get that. So what do I do if something like this happens? I picked this example on purpose.
You can apply current.
No, you can apply current, but then you still have a similar problem, because then your Y0 will be infinite.
Well, you can
Your
consider.
Z0 will be infinite, right?
Well, you can consider resistance instead of.
Yeah, just assume you put a resistor there, an arbitrary resistor. Let's say it's Rx. And redo the calculation with Rx. It turns out none of these three changes, because still they're 0. They're open, doesn't matter what resistance you have here. But now instead of this being infinity, what happens is that when it shorts, when both of them are shorted, Y is 1 over Rx. And of course, as Rx goes to 0, it becomes infinity. But let's keep it in terms of Rx, and then we'll set Rx to 0 at the end. And if you have a problem there, then you have a serious problem. But let's see if you do. And then the time constants. What is tau pi 0? Can someone tell me what tau pi 0 is? What is the resistance seen by C pi when this is open?
1 over Gn.
It's Rn, right? Think about the T model. Rm C pi. What is tau L 0? What is the resistance seen by this guy? When this one's open. What is it?
Rn plus Rx.
Rm plus Rx. tau, so we have to choose which one. I mean, we can, if you're in doubt, doesn't matter, just like pick one. I'm going to short this. So this is simpler, so I'm going to take it tau L mu, tau L pi. Since this looks a little bit simpler, very simple. So I'm going to short C pi, so this is connected to ground, so this will be ground. What do I see? Rx Cl. I'm done at this point. But, okay, now let's calculate the things. So y of s is going to be, so y0 is 0. Let's do the denominator first. So it will be this plus that, so I get Rm times C pi plus C mu plus Rx Cl times S plus this times that, which is Rm Rx C pi Cl S squared. Okay. And what do I get in the numerator? So these are all zero. The only thing I have is a second order term, which is this times that times that. Or in other words, this times that whole thing. So I get 1 over Rx here and I have Rx here. They cancel each other out, right? So I get Rm C pi Cl S squared. Okay? And now, I basically just, and what happens if I set Rx to 0? Well, everything that has an Rx in front of it, unless it's divided by another Rx, goes to 0, right? So this is 0. Well, I shouldn't have erased it, I should have just crossed it out. Yep, that's what I have. So that's my admittance. If I want my impedance, now, if I'm really interested in that, I just do it at the end. So I get 1 over that, I get 1 over Rm C pi Cl S squared plus this divided by that, so Rm's cancel, so I'm getting C pi plus Cl divided by C pi Cl over S. And this is actually an interesting quantity, right? This is the parallel combination of the two. Or really the series combination. Really the series combination, but I use this as an operator. C pi Cl S. So by the way, so whenever I do this, this is an operator. This means that half of the harmonic mean. Harmonic mean of A and B is 2AB over A plus B. So I define this as an operator. By the way, you know why it's called a harmonic mean, right? What?
For example, for a massive to solar system, when you want to calculate.
You mean the effective mass? Not the reduced mass. The reduced mass. Yeah, but the reason it's called harmonic mean is that actually, if you have a string, like a guitar or something like that, the frequency is the harmonic mean of the lengths. If you just basically, if you take the two of them and then reduce, cut them, pick the length that's between the two, called the harmonic mean. So, anyhow, so let's go back to this. What does this look like? What is the equivalent circuit for the input? What is this? This is simple. So yeah, it says at the input you see a capacitor in series with something. The capacitor is basically the series combination of Cl and C pi. Right? So this is the equivalent input resistance. What is this? What do you think that is? What is it?
A new element.
A new element. So we should call it. Well, it's kind of pretty much the same kind of naming scheme. It's a little less, it's a little bit more hypocritical, less honest. It's FDNR. it's like a super, and sometimes it's called a supercapacitor. Because it's like double the effect of a capacitor. But actually, if you look at the thing carefully and look at it in frequency domain, let's look at this. So what is 1 over s squared? Or k s squared? Well, in frequency, if you do j omega, what is this? This becomes minus 1 over k omega squared. So it's real, right? Because it's s squared. But it's negative. So it gives you what they call a frequency-dependent negative resistance, because it's frequency-dependent and it's negative resistance. It's a little bit more informative than A and E as well. But that's what it is, right? So this actually is useful. It says that if you make something with two capacitors like this, you can create negative resistance. And this is, by the way, how you make one of the ways to make it an oscillator. It's called a clap oscillator, for instance, right? I mean, a clap oscillator looks like this. There are variations of it, but if you put an inductor this is copins basically. This is the variation on copins. This is the common drain copins. What you have is that you have capacitance here, right? And inductance on this side, and you have negative resistance on this side that will cancel the loss, or the positive resistance on this side. Can cancel if you design it properly. And this thing can oscillate if you attach an inductor to it. Because this negative resistance cancels the loss. It's also used in making active filters. It's used a lot in making active filters. Because active filters you require sometimes to make L's and C's, so you basically can't compensate the losses with these elements. So these supercapacitors or FDNRs are used often making active filters. You can make high order active filters. Anyway, but you can see it easily comes out of the, oops,